Okay, just take a look at this. It's beautiful, right? So symmetrical, so complex. You'd think it's some kind of abstract art. But what if I told you it's not just a pretty picture? That this is actually a language?
I mean, what are we really looking at here? There's some kind of hidden logic. You can almost feel a rhythm flowing through those lines. So the real question becomes,
well, the answer is, it's kind of both. And over the next few minutes, you and I are going to crack this code together. We're going to learn the secret language that's hiding inside this beautiful, totally mesmerizing shape.
All right, so to really get what's going on, you first have to realize this isn't just a static drawing. Nope, it's actually the result of this amazing dance between two super simple motions.
So the official name for one of these things is a Lissajous figure. I know, sounds a little complicated, but trust me, the idea behind it is so simple. Just picture an Etch-a-Sketch, right? You've got one hand turning the knob that moves the little dot left and right. Your other hand is turning the knob that moves it up and down. Well, a Lissajous figure is just the path that dot traces when both hands are turning their knobs at the exact same time. That's it.
So that begs the question, how do we get all these different wild shapes? Well, it all just comes down to the settings on our two control knobs, those two waves working together. Let's break down the basic ingredients. You know, to create these incredible patterns, there are really only 4 simple dials we can turn. A and B, they control the amplitude, which is basically just how wide and how tall the final shape gets. Then you've got omega, that's the frequency, just a fancy word for the speed of each wave. And finally there's phi, which is the phase, that's just the starting point. Like, did one wave get a little head start? That's all phases.
okay, let's start with the absolute simplest case. What happens when both of our waves are moving at the exact same speed?
Okay, so if the speeds are totally matched up, the only thing we have left to play with is the starting point, that phase we talked about. And believe it or not, just by changing when one wave starts compared to the other, we can create 3 completely different shapes. First up, what if both waves start at the exact same moment? We call that a phase difference of 0. They just move in perfect sync, and the point, well, it just traces back and forth along a simple diagonal line. Easy enough.
But what if one wave starts just a tiny bit behind the other one? Let's say like an 1/8 of a cycle late. That's 45 degrees. All of a sudden, that boring straight line opens up and we get this beautiful clean ellipse.
And now for the magic moment. If we delay one wave by exactly 1/4 of a cycle, a 90-degree difference, that ellipse rounds out into a perfect circle. I mean, just think about that for a second. A perfect circle is just the result of 2 simple waves dancing perfectly out of sync. How cool is that?
All right, circles and lines are cool, for sure. But what about that super intricate pattern we started with? To get there, we've got to see what happens when the waves have different speeds.
Well, this is where the real fun starts. Because when the speeds are different, this incredibly simple and powerful rule just emerges. A rule that lets us decode any of these patterns, no matter how crazy they look.
Here's the secret. The ratio of the 2 wave speeds, it's written right there on the shape itself. All you have to do is count the loops. Seriously, the number of loops that touch the top and bottom tells you the speed of one wave, and the number of loops touching the sides tells you the speed of the other. It really is that simple.
Okay, so now that we have this new superpower, let's go back to our original puzzle. It is time to finally decode the hidden language of this shape. The hidden code, the secret ratio of the speeds that created this whole pattern, is 2 to 3. One wave is moving at a speed of, say, 2, and the other is moving at a speed of 3. But how can we be sure? How do we know? Well, let's use our new rule. First, let's count the loops touching the side, the vertical ones. Ready? 1, 2. Okay, got it. 2. Now let's count the loops touching the top, the horizontal ones. 1, 2, 3. 2 loops on the side, 3 loops on the top. The frequency ratio is 2 to 3. Boom, we've cracked the code. But look, this is more than just a cool math trick. Now that we actually understand the code, let's talk about why this matters in the real world. I mean, why do engineers and physicists care so much about these patterns? Well, these figures are basically a visual calculator. Imagine you're an engineer working with totally invisible forces, like sound waves or radio signals. These patterns give you an instant diagnosis. You can put 2 signals on an oscilloscope and bam, you can immediately see the relationship between them. Is one signal twice as fast as the other? Are they perfectly in sync or totally off? It takes all this complex, invisible data and turns it into a simple picture you can understand in a glance. So, what started out looking like a mysterious piece of art turned out to be a really precise language. one that describes how waves interact. It just goes to show you that even in the simplest, most repetitive motions, there can be this hidden order that creates absolutely breathtaking complexity. And it really makes you wonder, right? What other invisible forces, what other hidden languages are out there shaping the world all around us right now?